Okay, so it's a special pleasure for me to participate in this workshop because this is the first time I've gone to a workshop where the majority of the organizers are my scientific children. So, so I think I've always think that my best scientific accomplishment is that I'm still on good terms with my former postdocs and students, and this is one of the advantages that comes from that, getting to enjoy these talks the last couple of days. So I'm going to talk about topological materials. I just noticed recently this was the title that I had, about the relationship between topological materials, and I will mean for this talk three-dimensional time reversal invariant topological insulators and spintronics. Are these materials useful in spintronics? And we've all learned in the last couple of days and have been aware that more and more materials are useful in spintronics, everything but the kitchen sink. So it's a pretty good bet that topological insulators will have an interesting role in spintronics. And many of the materials on that list are interesting because of spin-orbit coupling effects, especially spin-orbit coupling effects that occur at interfaces. And the basic property of time reversal invariant topological insulators is that they are in some sense in the extreme limit as far as spin-orbit coupling is concerned. Because of the topological nature of the band structure, the surface states of topological insulators are non-degenerate. The spins are completely split except at time reversal invariant points in the surface Brouin zone, for example, the gamma point. And that splitting, if we have magnetism, and as I will discuss magnetic topological insulators mainly, even that splitting can be lifted. So we have no spin degeneracy at all. All of these, at least the surface state bands, which are the bands closest to the Fermi level and normally thought to be the important bands in modeling spintronic effects, are completely spin orbit split. And also these bands have the spin state, as you can see from this Dirac model. So here tau is a Pauli matrix for spin in this equation. And so you can see that the direction of the spinner depends rapidly on k, and there's a large momentum space Berry curvature associated with that, and that will figure prominently in the effects that are interesting and that I'll talk about. Okay, so as I said, spin-orbit coupling is important for many of the things that are currently interesting in spintronics. This is one. If you have a uniform ferromagnet, normally we think that it's hard to manipulate with a transport current, but as we know from work over the last 5 to 10 years, starting from this pioneering paper by Miron et al., when you have spin-orbit coupling, you can manipulate even a single uniform magnet with a current because of if you want to think of it that way, spin or angular momentum being transmitted from the lattice to the magnetic order parameter or vice versa. So that's it. Spin-orbit coupling is important. Topological insulators, at least topological insulator surface states, have very strong spin-orbit coupling. So it's natural to think that this spin-orbit torque type effect might be very strong in topological insulators, and indeed that was the property that was demonstrated first, I believe, by Yabin Fan et al. From Kang Wang's group, and Priya who is here, was one of the people who was involved in this work in his previous life as an experimentalist. And they demonstrated that the spin-orbit torque coefficient, which is the number of the rate at which the spin torque, or spin rate at which spins would change from the spin torque to the in units of h bar to the charge current in units of E. So this is often used as a figure of merit for the efficiency of current-induced torques in magnetic systems. Of course, in spin transfer type torque phenomena, which is based on conservation of total spin angular momentum, the maximum possible value of this coefficient is 1. And this experimental work has demonstrated that this figure of merit, if you like, is thousands in topological insulators. So indeed, there is experimental evidence that topological insulators are very have very strong spin orbit torque effects, at least. Okay. So I'm going to spend most of my time talking about some ideas around that observation. The starting point, I'm going to talk about, therefore, a theoretical formulation of current-induced torques in systems with spin-orbit coupling, and it's a commonly used one. It's based in the first place on separation of the degrees of freedom of a system containing a ferromagnet into a collective order parameter degree of freedom and Fermi surface, if you like, particle hole type degrees of freedom if it's a metal, or as we'll see, interband degrees of freedom are also probably important. And in ferromagnets, we can easily have a picture where we kind of rigorously separate these two types of degrees of freedom in as long as the order parameter varies slowly in time and space. Okay? And so one of the important equations, and this is the equation I will that I think about when I think about the current-induced torques. This is an equation for the time dependence of the magnetization when, for some reason, either driven or it's been taken out of equilibrium, and so it has a time dependence, and it processes, as this equation describes it, processing around an effective field and decaying towards equilibrium, towards the lowest energy state. So it's the right-hand side of this equation is our torques that act on the order parameter. This torque in a metal is mostly due to the coupling to the quasi-particle degrees of freedom, the damping torque. And so the torque depends in this equation not on everything you might ask about whatever the non-equilibrium state is, but just the direction of the magnetization. And that, I guess, means that we're thinking and that when we apply this type of equation, that it's always the same non-equilibrium state. And so one could talk a lot about this equation, but for me, the definition of a current-induced torque is just that the right-hand side of this equation changes when the value of the right-hand side of this equation changes when you have a current. And that's what we want to calculate. It changes because the current changes the non-equilibrium state that the system is in when it has a particular magnetization. So when people talk about these current-induced torques due to spin-orbit coupling, it's common to separate them into two different cases, and I will just for simplicity always consider the case, or mostly talk about the case where current is flowing through some stack along a direction I'll usually call the x direction, and I'll mostly assume that the magnetization is parallel to the current, just for definiteness. And one effect that occurs in these systems is that when a current flows through just any old conductor, there's a current-induced spin polarization because of spin momentum locking. I didn't emphasize that yet, but obviously that's very important in topological insulator surface states, and potential that can create a current-induced spin density, and the magnetization will precess around that spin density. There's another effect that is normally described in this way, which is the spin Hall effect. If you think of a current flowing through a conductor with strong spin orbit interactions, then there can be a spin Hall effect, which in some cases you can describe in terms of a spin accumulation on the top and bottom surfaces, which will drive a current, a gain of spins pointing in the y direction. But these currents are flowing into the ferromagnet, and in the steady state, because this current will decay in the magnet, it turns out that this spin polarization associated with the spin Hall effect will be in the z direction. Okay, so it will that will produce an effective magnetic field in the z direction, or that will allow the exchange interactions between these itinerant electrons and the order parameter to make this current decay and transfer ultimately this spin into the ferromagnet. Okay, so okay, I'm going to say this again in a second. So this is just a cartoon about this point of view. To calculate current-induced torques, we need to calculate for a given exchange field in a ferromagnet, how the spin density in the system is changed by having a current flow. And when I have this, let's say, current or electric field induced spin density, in the quasi-particles, the order parameter will have an exchange interaction with this spin and will precess around it. And so, right. Okay, so next thing I'm going to say is that both of these effects always exist independent of any microscopic picture. And so just by symmetry considerations, which we can explain in this simple way. So we have lots of spin-orbit coupling. So let's say I want to calculate a magnetization in the y direction that's induced by electric field in the x direction. And I'm just looking at the mirror symmetries of this response function. The magnetization in the y direction, because of spin-orbit coupling, I don't need to distinguish spin or orbital angular momentum, so I can just write this as px times z. That's the pseudovector magnetization component. Y component is a product of an x component of a vector and z component of a vector. And this is even in x, even in y. It doesn't have to be even in z because we've broken inversion symmetry just by the structure of this thing. So current-induced spin polarization in the y direction is allowed by symmetry. It's always there, independent of microscopic mechanism. So what is normally identified as a spin Hall torque is a spin polarization in the z direction that's induced by, let's say, electric field in the x direction. If I write down for the z component of the magnetization pseudovector a product of a y component of a vector and a z component of a vector, you can see that this is odd, for example, under y go to minus y, which is a symmetry of the system. So I can't have a spin Hall. I can't have the magnetization that corresponds to a spin Hall torque unless I add another term which represents the way the quasi-particles respond to the order parameter. So here I've added an order parameter which is couples to x component of the spin density, and you can see that this spin Hall type current-induced spin density is allowed. So both of these current-induced quasi-particle spin densities and associated torques are always there, irrespective of the microscopic picture. And in the case of topological insulator surface states, if we think we can model what's going on by just looking at the physics of the surface states, then it's not clear, what we would mean by a spin current flowing vertically through this system. And it's not clear what we would mean by spin accumulation, which is certainly not a relevant concept in this case, because the energy, as I was saying, energy of every band state has a particular spin orientation, and there's no spin degeneracy at all. So I can have something that's phenomenologically just like a spin Hall spin torque when it's not spin Hall effect. And topological insulator surface states are an example of that. And maybe these mechanisms are also active in some of the other cases that are studied experimentally, for example, ferromagnets on tantalum or platinum. Okay, so if we want to calculate the current-induced quasi-particle spin density in the presence of the order parameter, coupling to the order parameter, to the magnetization, then we have to do some kind of transport theory. And here I've written down the kinetic equation for the density matrix of states in a crystal in the presence of an electric field. And there are three terms that cause the density matrix to evolve in time. One is just the free particle evolution. If I have, I have a density matrix component that's off diagonal in eigenstate representation, because the two eigenstates have different time dependence, it will have some time dependence. Then there's the electric field driving term, as I'll emphasize in a moment, and as is almost always the case, we can treat the response to the electric field at first order in electric field, and so when we do that, the coefficient of electric field here is the wave vector dependence of the non-interacting density matrix, and And then there's a collision term, which in general is quite complicated, but I'm going to assume I can, for the qualitative points I make, that I can use a relaxation time approximation. Okay. We can distinguish, especially if I have a system with a Fermi surface, if it's a conductor, then in the transport theory I can distinguish two types of response. Response at the Fermi surface and response off the Fermi surface, if you like, or response of density matrix components that are diagonal in a band eigenstate representation and those that are off diagonal. The driving term comes from the dependence of the density matrix on K, and that comes from the fact that I have a Fermi surface. The occupation probability depends on K when I cross the Fermi surface. That's the thing we usually take account of in the transport theory of metals. But there's another term that can be important if off-diagonal response is important. So one of the themes of this spin Hall-like current-induced spin density is an example of a response that is dominated by, which is really this off-diagonal response. And so one of the things I've been interested recently is finding examples where that kind of response is important physically, even in a metal. And I think this is one example. Another example is the chiral anomaly in Weil semimetals. Okay, so so we're going to separate the Fermi surface response and the non-Fermi surface response. The non-Fermi surface response the driving term, the density matrix depends on K, and that happens because the band eigenstates change as you move through momentum space. So this is related to what people normally describe in terms of Berry phases and so on. Okay. In the relaxation time approximation, at least, for the Fermi surface response, the driving term gets balanced against the relaxation term. And therefore, it turns out that the density matrix response at the Fermi surface, as you all know, for a metal is proportional to the transport scattering time. And if the relaxation is slow, the response is strong. But for the off-diagonal response, the steady state is established by balancing this free particle evolution, which is basically, if this were just a spin, a single band system with a spin, as it will be in a moment for the topological insulators, this is just spin precession, and is balanced against the time dependence due to spin precession is balanced against the time dependence due to the fact that the electric field is moving you through momentum space, and the spin direction of the eigenstates changes as I move through momentum space. So it's not, the off-diagonal response is not proportional to the relaxation time, okay? Normally. Okay. So I'm going to say some things about this off-diagonal response in a crystal, and so I'm going to make some comparisons just to get you used to it. So this is a little calculation. I took this off of an article on the web on the polarizability of the atom, which is one of the things we calculated in our first course in quantum mechanics. And if we do that in perturbation theory, then we find that in perturbation theory, the mean value of position inside an atom moves away from the nucleus if I have an electric field, and I can write the polarizability in terms of this perturbation theory, which involves matrix elements of position operator between the state we're interested in, say the ground state, and all the other states. And there's another way I can write this equation. Since the velocity operator is derivative of position operator with respect to time, I can write the commutator of the velocity, which is the commutator of h with respect to position. So I can write this for that, because if I make that replacement, I can write this in terms of velocity operators if I put in extra energy denominators. Okay? It's just the exact equivalently way of writing things related to gauge invariance. And it turns out, of course, we can write the same thing, same expression down for the polarizability, or what we would call the dielectric function of a crystal. Okay? And normally we don't write it in terms of position operators because they're not so well defined in a crystal, but this is the same expression, but this is not the actual, this is the response of the density matrix, which when you take an expectation value will give you the dielectric function of a crystal. It's just this normal perturbation theory expression, and it's obtained in a crystal just by balancing the the free particle evolution with the moving through k-space. Okay, so it's the same thing. There's nothing strange, of course, about having response away from the Fermi surface, normally it doesn't give charge flow, of course, although quantum Hall effect is an exception, but it can give things like charge density response. What's important for what I'm going to say is we're interested in spin density response. And also, you can get spin density response. Okay? So the spin density response that I'm going to calculate, which I'm going to associate with the torque, due to polarization, mixing of different bands, occupied and empty bands, is very much like the polarizability of a crystal. It's a spin polarizability, if you like. Okay. So I want to say something about numbers. This is the response that I get on the Fermi surface from the normal transport theory I described, where delta is how far particle moves in phase space in a transport scattering time. So if I want to identify, if I want to identify a dimensionless parameter that should be small for linear response to be valid, I could say it's this shift in momentum space compared to the Brouin zone size, and that's that you can rewrite as the electric potential across one unit cell, let's say, compared to the energy uncertainty, ratio of that to the energy uncertainty of the block states due to momentum scattering. And even in the big electric fields that often are used in these current-induced torque experiments, the value of the electric field drop across one unit cell is typically maybe 10 to the minus 6 eV, whereas this h bar over tau is typically some number of milli-electron volts, so we're in linear response regime. And as you can see, the off-diagonal response, the corresponding thing to compare this electric potential with is some interband electrical energy scale, like the bandwidth or the gap or something like that, whatever it is. In the case of topological insulator surface states, this scale will be the gap created in the surface states by coupling of the quasi-particles with the order parameter. And typically, if you have a good metal, this energy scale is much smaller than this one, and so the Fermi surface response dominates. So there has to be something special going on for the Fermi surface response not to dominate. Okay. Okay, so now to go further, I have to take, I'm going to take a simple model, which is approximate model of the surface states of a time reversal invariant topological insulator. I've written it down actually for the case where the magnetization points in the z direction. That's one of the interesting limits to consider. I'm mostly going to talk about the case where the magnetization points in the x direction, sigma 1 in this notation, and delta here is the exchange coupling between the quasi-particles and the magnetization. And so the Dirac cone that I would have for a time reversal invariant topological insulator, when the topological insulator is coupled to some magnetic system, of course, that breaks time reversal symmetry, and I get an additional term, which looks like an effective magnetic field that points in the direction of the magnetization, whereas the band structure, surface state band structure, if you like, has a momentum-dependent effective magnetic field, which it's momentum-dependent because it's represents spin-orbit coupling. Okay, so I mentioned at the beginning that one of the experimental observations is that that when you make a topological insulator magnetic by doping it, that's the simplest way to couple to break time reversal symmetry in a topological insulator. Then the figure of merit for the spin-orbit torque is the largest value that's ever been measured in any type of material. And it turns out that if you use this Rashba model, then the figure, you can write down an expression for the figure of merit with, again, without doing any theory, really. And the reason you can do that is because you can see that the velocity operator, which is the derivative of the Hamiltonian with respect to momentum, is basically the spin density. Okay, so so there's a very simple relationship, independent of the details of the theory, between spin density in one direction and between current and spin density. So this is the simple expression you can write down for the torque in units of h bar divided by the current in units of numbers of electrons. How much torque how many spins can you flip for every electron that you move through the system? And if you use this simple relationship between spin density and velocity of the electrons, it turns out that this figure of merit for the case of this R stands for Rashba. This is the figure, this is the expression for the spin density, the Rashba spin density, the spin density that's in the plane of the surface. And it's just the figure of merit, what people often call the spin Hall, or the angle, if you like, is the ratio of the gap of the size of the exchange coupling to the surface state quasiparticles divided by h bar divided by the transit time across the system, the energy uncertainty associated with the fact that it takes a finite amount of time to go across the system. So, so this clearly can easily be much, much bigger than 1. So it shows that these materials do certainly potentially have extremely large values for this Rashba coefficient. Right, so if I take this Rashba model and apply the transport theory I was describing before, then let me consider the case in which the so let me consider a case of electric field in the x direction. Then because of course when you have electric field in the x direction, you have more states with positive velocity in the x direction on the Fermi surface occupied than negative, states with negative velocity. And because of spin momentum locking illustrated in this cartoon, that will give a transverse spin density in the y direction, whose ratio to the current is given by the expression I just showed on the previous transparency in this model. But in addition, there is will be in this model a spin density in the z direction that is induced when the magnetization is in the x direction, that's induced when when the bioelectric field in the x direction. And you can understand that in terms of, because what happens then, as I was saying before, is basically in the steady state at every k, the spin at a given k will no longer be parallel to the effective magnetic field that you have at that k. And in order to produce a precession of the spin at that particular k around the effective magnetic field that just balances the time rate of change of spin at that k, due to the fact that you're moving to another k with a different spin orientation. So that's the balance, and it turns out that that gives a spin. This is an interband response. In the spin language, it's a spin density that's off diagonal in a eigenstate representation, because it's a perpendicular, or has a component perpendicular to this effective magnetic field. And it turns out that what survives when you sum over all k is the spin in the z direction. And as I said, from the general symmetry argument at the beginning, that only survives when I have broken time reversal in the system. And so, it turns out, as I'll emphasize again in a moment, I should have put the slides in different order, I realized, that in fact from experiment, it's that spin density that's largest, okay? Yes, yeah. And the...
But why? I mean, if you dop it higher, then you're going to have the other one dominate eventually because the energy cost.
So I will comment on this. So I mean, I think it's a good, as I'll say, it's a good question. So the okay, so just some details that are involved in modeling these experiments. So the surface states of a topological insulator in this Dirac model are coupled to a magnetic order parameter, so they have broken time reversal symmetry. If you carry out, these details of the transport theory I outlined, you get a resistivity tensor that looks like this. It depends it depends on the azimuthal orientation of the magnetization in the xy in the plane. That's what these angles phi are, and it has both symmetric and antisymmetric off-diagonal components of the resistivity tensor. The the current doesn't go in the same direction as the electric field because of anisotropic magnetoresistance for general magnetization direction, and also because the Hall effect. And you can calculate all of these coefficients from the transport theory. And the form of this tensor looks like what's normally assumed in theory of magnetoresistance in a bulk metal. Of course, it's not a bulk metal. It's this is a 2D metal, and so it turns out that the dependence of this resistivity tensor on the component of the magnetization out of the plane of the 2D system is not determined just by symmetry and has to be calculated explicitly. And so you can calculate all these response coefficients, including the Hall effect, which is of course maximized when the magnetization is out of the plane, and the anisotropic magnetoresistance, which is maximized when the order parameter is in the plane of the 2D system. So all of those things enter the theory, and in general, in order to get a net torque on the magnetization, it turns out that you don't want the magnetic order parameter to couple equally to the top and bottom surfaces. Then everything will cancel out. Usually it's grown so that the magnetization is only connected to one of the two surface states. But you can consider some general situation, and usually you're interested in a case where one surface, let's say top surface, has a Hall effect, bottom surface doesn't have a Hall effect, and the direction of the electric field has to be the same everywhere in the system, you can argue. If this direction is the current carrying direction, then the total current between the two surfaces that's carried in, across the slab has to be zero. That determines the direction of the electric field. And when you put all this together, actually one of the interesting things that comes out of these observations is that there must be a current circulating around the edge states of this topological insulator in this experiment. I'm not sure if it's observable, but it might be interesting if it could be. I think it probably is observable. Okay, so I'm not going to go through the details, but if you just plug all of those ingredients in, this is actually, these are the results that you get not for the real geometry of the experiment, but for electric field in the x direction, where you have an in-plane Rashba-like current-induced spin density and an out-of-plane spin density, which would produce a torque of the same in the same direction as people would normally call a spin Hall effect. And you can see, you can write, I wrote this as a dimensionless thing, spin density compared to electron density, assuming that the Fermi level's not in the gap. These expressions only apply in that case. And so this is the ratio to of the spin density to the number of electrons in the system. You can see that the denominator here, as I was arguing before, is h bar over tau for the Rashba thing, which is a Fermi surface response from spin momentum locking. The denominator in the for the z component of the spin density is some scale. It's hard to say whether you should put here the in when you have squiggly lines, if it's better to put the energy gap of the bulk energy gap of the topological insulator or the surface state gap, but they might be rather comparable anyway. And this is only non-zero if you have a an order parameter present, so you get, it turns out you get another factor of exchange splitting divided by Fermi energy, which might be of order 1. So, these systems are not such great conductors, so h bar over tau is not so big compared to the gap. So you might guess that these things are comparable, and in fact, in comparing with we can't really compare with experiment because, for one thing, we don't know the carrier density in this experiment, which is important in the theory. We know the conductivity because that's been measured. So we know the product of the Fermi energy and the scattering time. And most of all, there's a controversy about the size of the exchange splitting of the surface state quasi-particles in the magnetically ordered state. So that's not really nailed down yet. But if you sort of take the guesses and the estimates that are in the literature at the moment, it turns out that you get you can get reasonable agreement with experiment. And the experiment really measures the ratio of the current-induced spin density to the total spin density of the ferromagnet times the strength of this exchange coupling. The number that comes out of the experiment is about, for this number, is about 10 to the minus 6 eV. So this ratio at the electric field the experiments were done then would have to be about 10 to the minus 5 or so. And that's plausible based on what we know. Okay? In this, it's plausible that that can be explained just by this Dirac theory. And the other thing that is claimed in the experiments is that the spin Hall-like torque is much bigger than the Rashba torque. And this can be true in the theory. Of course, this is very much true in the theory if there's no Fermi surface response. In other words, if the Fermi level lies in the gap, or if the Fermi level lies in a region where, for example, of quite localized states that aren't very conducting. So if this experimental result holds up, and I know there are other experiments from Dan Ralph's group, but I haven't actually seen a paper myself yet. And so we'll have more confirmation of this. But so these results suggest that, may suggest that, these particular experiments were done with Fermi level nearly in the gap. Okay. I won't go through this, but if you put in the numbers, I was saying the experimental findings make sense. That's all you can say at the moment, mainly because we don't really have a widely accepted number for the strength of the exchange coupling between the order parameter and the surface state quasiparticles. Okay, so I have 5 minutes maybe. I'm just going to say a couple of things really quickly. So according to the experiment, it's this interband insulator-like response of the spin density that is dominating in the experiments done on the topological insulator surface states. As I said, that type of spin response is allowed just by symmetry. And this, for example, is a toy model of an insulator. What this is an atom, a toy atom, which has basically spin orbit coupling, has atomic energy levels kind of platinum, and it has spin orbit coupling strength of platinum, but the number of occupied d orbitals is varied. It has and this atom has an external magnetic field, which we imagine in practice is the exchange coupling of that particular atom to the magnetic order parameter. And also it has an electric field in the z direction, and we imagine that coming from its position at an interface that breaks symmetry. The bands realign at the interface, and it has, and this is the linear response of the spin density for this atom in the z direction. When the exchange field is pointing in the x direction, this is the linear response in the z direction to an electric field in the x direction. So if you put in sort of numbers from this, it's not crazy different from the size of the torques that people, if you had this scale of spin density response for every surface atom of tantalum, it's not crazy different from the size of the torques that are measured. So this kind of effect, interband effect, may well be playing a role not only in the topological insulators where it can be the only thing, but also even in metals. So finally, let me mention the case, another property of topological insulators that has got to do with away from Fermi surface response, and that is their magnetoelectric or multiferroic properties. This beautiful illustration is, I think you all recognize from this paper by Shuqing Zhang and collaborators, and they pointed out that if you have a perfect topological insulator with infinitesimally broken time reversal symmetry at the surface, then you get a half quantized Hall effect and on the surface, and the currents that are associated with an electric field perpendicular to the surface give a magnetic field like that from a magnetic monopole, which is kind of entertaining. Of course, this is actually completely academic because this field theory model completely neglects the fact that in practice the surface of a topological insulator has a longitudinal resistivity, and so this effect becomes, when you include that, becomes some transient effect that you might be able to see on some time scale if the longitudinal conductivity is sufficiently small. But it does emphasize that there's some relationship between topological insulators and magnetoelectric materials. And our normal way of characterizing a material is in terms of Maxwell's equations. Maxwell's equations still work. When we have a medium, we have to include the total charge density, including changes in charge density in response to electric fields inside and magnetic fields inside the material, and currents that are flowing inside the material. And that so-called topological magnetoelectric effect I just showed you can be described by a field theory model where you add a term to the Lagrangian that looks like magnetoelectric coupling. You put a E dot B term in the Lagrangian, and it can give you that magnetic monopole effect I was just mentioning. And if you look at, if you take that Lagrangian and calculate its equations of motions, then you find that it's not, that Lagrangian with the E dot B term has different equations of motion than the usual Maxwell's equations. There's an extra term that's written here, but you can see that this extra term is just like saying that there's a current that's perpendicular to electric field, and that is present whenever the magnetoelectric coefficient changes in space. So for example, if I say I have a material like a topological insulator, and I have a non-zero value for this E dot B coupling inside the material, then when I go across this interface in this direction, then there's a gradient which has one sign, and when I go out of the material down below, there's a gradient that has the other sign. And so this current perpendicular to electric field on the surfaces of the material is a surface Hall effect, right? So this electric magnetic field coupling is exactly the same as saying I have a surface Hall effect. And but if I really want to use this model and take it literally, then it can only describe, because if alpha is non-zero inside the material and zero outside, then I have to have opposite surface Hall conductivities on the top and the bottom. And so that means I have to have magnetizations opposite on the top and the bottom. That's a situation which we can now realize. And so it turns out that if you have a 3D topological insulator and you have a magnetic layer coupled to the top surface and coupled to the bottom surface, it becomes a real gap system with gaps everywhere on the surface. And so it's a real dielectric, pretty bad one probably, but a real dielectric. And it also is, as you can see from this equation, it's phenomenologically a multiferroic material with a response of polarization to magnetic field and response of magnetization to electric field. And all of that response, if you think about it, since everything's insulating, comes from states away from the Fermi level. Okay, thanks very much.